Welcome to this, the final lecture for Unit 5, in which we'll be looking at cosmology. This is a very famous photograph, part of it anyway, taken by the Hubble Space Telescope. It was taken of a very small section of the sky that looked like it was dark, and Hubble Space Telescope was trained on that area for a long exposure photograph, and what we see that in what appeared to be just a dark region of the sky is actually full of galaxies and systems, so there's a lot of stuff out there. Anyway, we're going to look at some of it during the course of this lecture. We're going to start by looking at the cosmological principle, which was actually first clearly asserted by Isaac Newton. So the cosmological principle says that if you look at a sufficiently large scale of the universe, then the properties of the universe are the same for all observers here on Earth, and if you happen to be in another galaxy, then it would appear to be the same for you as well. Okay? So what this is essentially saying is that the part of the universe that you can see and observe and take measurements for is a fair sample. Okay? So the same physical laws apply throughout the universe. The two key terms that you need to know are, firstly, the universe is homogeneous, so it's evenly distributed, and that is true over large volumes. There's a lot of space, so there's lots of empty space or space with just a few atoms in it, but if you take a particularly large volume, then the universe is homogeneous. It's also isotropic. That means that the physical properties are the same, such as temperature. Temperature is a very common example for this. So isotropic and homogeneous. So wherever you look in the universe, the physical laws are the same, and there appears to be the same stuff there, obeying those physical laws. So what this means is that the universe is playing fair with scientists. When we take our measurements and we're trying to see what applies throughout the universe by observing what we can here from here on Earth, then the measurements and observations we make, they are valid throughout, and the conclusions we draw from them as well. Right, astronomical objects. So we're going to look at the various types of objects you can have with it, including the universe. So the first thing is the universe is everything. Okay, everything physical is in the universe, and so that's like at the largest scale. Then within that, and this one you wouldn't particularly need to know about, but you have galaxy clusters. So those are groups of millions or even billions of galaxies that are all clustered together, and they, to some extent, interact with each other. They act like a system. Then you have galaxies within those, and galaxies are clusters of billions, hundreds of billions of stars. Our galaxy is called the Milky Way. That is not a picture of the Milky Way. That's a picture of Andromeda, which is our nearest neighbour, or our neighbouring galaxy. Now, the reason why no pictures of the Milky Way from outside exist is because we've never gone outside the galaxy. We've never sent any probes outside the galaxy to take photographs of our galaxy. So we can take pictures of the Milky Way from within, and there are pictures out there that exist, but none from looking in. And yeah. The solar system, that's the sun, which is our star, star in our system, and the planets. There's also a dwarf planet. Pluto was recently reclassified as a dwarf planet. There are moons, which are natural satellites, comets, which are frozen dust and gas, and then asteroids as well. And I've just remembered what I wanted to say. The furthest probe that we've ever sent out, or the probe that has travelled the furthest that we've ever sent out, I think it was last year, actually left the solar system. So that's as far as we've sent something that has just recently exited the solar system. And if it's going to exit the galaxy, it's got a heck of a long way to go yet. And then you need to know the planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune, that's going outwards from the Sun. By the way, this diagram is not to scale. Okay, a little bit more about the Earth and the Moon. The Earth makes a complete rotation about its axis in 24 hours. Should know that, hopefully you do. The Moon is a natural satellite for the Earth. It's the only natural satellite for the Earth. And it takes 27.3 days to complete one orbit of the Earth. Interestingly, the Moon's rotational period is about the same as its orbit, so that means that the same side of the Moon faces towards the Earth at all times. And the far side is always on the far side, so it's always facing away from the Earth. It's not the dark side because the Earth is not emitting the light that illuminates the Moon. The Sun is, and so as you know, during a total eclipse, a solar eclipse, the Moon has come between the Earth and the Sun, and therefore that far side must be pointing towards the Sun and being illuminated. So it's not the dark side of it. Right, now space is big, really big. So it's handy to have some practical units to take some measurements. The first unit we'll talk about is the astronomical unit, called the AU. That's the mean distance between the Earth and the Sun. It's the mean distance because the Earth is not always the same distance away from the Sun. So I've got a slightly elliptical orbit to represent that. Probably somewhat exaggerated. And the mean distance, so that 1 AU is 1.5 times 10 to the 11 metres. And what you would use that for is if you're talking about objects within the solar system. So Earth to Saturn is 9.02 astronomical units. So that's the astronomical unit, it's the first one. And we're also going to use that to derive the third practical unit when we come to it. Next practical unit is the light year, LY. This is the distance travelled by light in 1 year. It's important to note that it's a unit of distance, not a unit of time. So there's my light photon. It's travelling at c, 3 times 10 to the 8 metres per second. And in 1 year, it will have travelled 1 light year. So c is 3 times 10 to the 8 metres per second. The time that it's taken to travel this distance, the light year, is 365 times 24 times 3,600. That's 3.15 times 10 to the 7 seconds. So 1 light year is the speed multiplied by the time. That's 9.5 times 10 to the 15 metres. And you would use that for distances of stars, either from the Earth or from the Sun. Sometimes you would take measurements from the Sun because that's the fixed object for the solar system. Of course, the Sun is moving, but we all move in a regular way with the Sun. So, Sun to Alpha Centauri is 4.37 light years, Alpha Centauri being another star. Okay, so that's the second practical unit, that's the light year. Then we have the parsec, which is PC. A star which has a parallax, and I'll explain what a parallax is. A parallax of 1 arcsecond is defined to be 1 parsec distant from the Sun. Stellar parallax is due to the shift in position, or is the shift in position, of a star due to the Earth's orbit around the Sun. Okay? So the Earth is orbiting around the Sun. We know how far away, or what the radius of that orbit is. That's 1 AU, okay? The mean distance, but still. In 6 months, the Earth will have completed half of its orbit, so it'll be on the other side of the Sun. And if you're looking at a star in the sky, you'll be looking at it from one angle here, and then when you've moved to this side of the Sun, you'll be looking at it from a different angle. So stellar parallax, which is the P, that's the half angle through which the star's direction changes. Okay, so that means that the complete angle here between these two lines of sight to this star that we're interested in is 2p, and half of that is the stellar parallax. So if the angle in these two lines of sight is 2p, then that star is defined as being 1 parsec away from the sun. Okay, because it's going to be this distance here that we're measuring. So that's sun to the star. P, 1 arc second, is 1/3600th of a degree. So we know what P is because we're defining this distance, the parsec. And that means that 1 parsec, if we use trigonometry, this distance here is going to be the tan, or tan P, or we're going to use tan P, and the opposite is 1 AU. So this distance is 1 AU over tan P. Therefore, if we put our numbers in now, we know what the astronomical unit is. It's 1.5 times 10 to the 11. Put in tan of 1 over 3,600. So that's tan of 1 arc second. That gives us 3.1 times 10 to the 16 meters. And the parsec is used for the largest astronomical distances. So, for example, Andromeda is 778 kiloparsecs away. All right. Note the use of prefixes here. I've used the prefix, so that's 778,000 parsecs away. And megaparsecs is also common, so that would be 3.1 times 10 to the 22 meters. So using a larger unit there. Those are the practical distance units, and you'll see particularly the megaparsec and parsec being used in a few places later on. Right, let's now look at Olbers Paradox, who was Olbers was a German astronomer, and at the time of Olbers, the universe was thought to be infinite and static. Now, Olbers thought there was a problem with that. So this is his paradox, is that there's a problem with the idea that there's an infinite and static universe. In an infinite and static universe, he said that all lines of sight should eventually end on a star. And so the night sky should look like this, light, because eventually your line of sight will end on a star. And so you should have a light night sky. But the sky at night is dark, and therefore there's a problem. And because the night sky is dark, that means we can't be in an infinite and static universe. Okay, that was an animation that I found online, a very useful one, illustrating what the sky should look like. What conclusions can we draw? The night sky is dark, so the universe cannot be infinite and static. So the universe is finite. There is an end to the universe, and beyond that, there are no stars and galaxies for your line of sight to end on, no sources of light to end on in some lines of sight. And therefore, you get a dark nighttime sky. Also, because there's a finite number of stars, because there's not an infinite number, so there is a finite number, the total energy is too small to make the sky light. And we will also see that there are reasons based on the fact that the universe is expanding. Okay, we're going to see that the universe is expanding. If the universe is expanding, it's not static. Okay, and if the universe is expanding, some stars and galaxies are moving away from us too fast, so that the light will never actually reach us. Even if we're looking at a line of sight that should eventually end on a galaxy or a star, if it's moving away from us so fast that the light can't reach us, then that line of sight will be dark. So the conclusions are that the universe, or the main conclusion is of Olbers Paradox, is that the universe is not infinite and static. Okay, so that's Olbers Paradox. Let's look at redshift. The redshift, and what I'll do here is explain what the redshift is, and then we'll see some conclusions from the redshift when we go on to the next slide. Light from distant galaxies, so these are galaxies that are very, very distant, is redshifted. the light, and when I say redshifted, that means that the light has increased its wavelength compared to what it was when it was emitted. So the wavelength has changed since it was emitted. And we know it's been redshifted because of the absorption spectra in the light. So now remember that absorption spectra for elements, they are unique. So we do have a way of checking this. This is the absorption spectra from a lab source. Now I just made it up to illustrate it, okay? So you can see the dark lines in the visible part of the spectrum. This is the same absorption spectrum, but it's from a distant galaxy. It's been emitted, the light was emitted by a distant galaxy and it's absorbed, some of the wavelengths were absorbed. That light has since then reached us, and you can see that the positions of these dark lines, they've changed. They've been shifted towards the red end of the spectrum, okay? So this line was in the green region, but it's been shifted into the yellow and orange part of the region. So it's been shifted towards red. It doesn't mean that the light becomes red, like these wavelengths here, they were in blue, they've been shifted into the green, okay? So it's not become red, it's been shifted towards the longer wavelength end of the spectrum, okay? So by using these unique spectra, we can identify this shift in the wavelength, okay? And this redshift is a type of Doppler effect. You can also have blue shift as well. It's possible to have light that's shifted towards the blue end of the spectrum, but you don't receive those from distant galaxies. You can receive them from objects within our own galaxy, blue shifted, but not from distant galaxies. This indicates that if I shift this spectrum along a certain amount, then I can line the lines back up. So you can see there's a shift in wavelength, and then you can use that change in wavelength to work out the speed of the source, whether it's towards or away from as well. So if it's redshifted, it will be like this. In this case, the wavelength has increased. That will give us the velocity moving away from us. Okay, so that's the redshift. That's how we know that the light has increased its wavelength. Now I'm saying here also, there's a type of Doppler effect. It's not quite the same as Doppler effects that we've already seen. Here, instead of the fact that we're moving away, in a normal Doppler effect, the Doppler shift would happen at the source. Okay, so as the wave is emitted by an object moving away from us, the wavelength is increased. But here, what happens is the change in wavelength happens as the light travels through space. Because space is expanding, it increases the wavelength. Okay, so it's slightly different, but this equation can still be used to determine the speed. Let's move on to consider Hubble's discovery here. He discovered that, well, we know that light from all distant galaxies is redshifted, and that means they're all moving away from us, all these distant galaxies. There are some stars within our galaxy, so they're being affected by local gravitational effects. So those ones are blue shifted, but distant galaxies, that light is red shifted. So they're moving away from us, and I showed you the equation so you can deduce that they are moving away. Beyond that, Hubble discovered a relationship between the distance between us and a distant galaxy and its speed at which it's recessing from us, so the speed that it's moving away from us. He discovered that they are directly proportional. And that also applies, if they're all moving away from us, they're also moving away from other galaxies as well. Okay? So if we take, and Hubble, yes, I didn't say who Hubble was, he's a US astronomer. And so let's look at these galaxies that I've got here. Okay? They all start at distance d apart. We've got our 5 galaxies, and we're there on the X now. Here we're bang in the middle, but we don't necessarily have to be in the middle. In the same amount of time, all of the galaxies move so that the distances between the galaxies, which all started off at d, they all double. Okay? So all of the distances double. The speed of recession is directly proportional to d, and Hubble's constant is the proportionality constant there. So that's h naught. That's the proportionality constant. And this relationship between speed and distance implies or arises because all of the distances between the galaxies have doubled. So when you have something like this where all of the distances between the objects double, which arises because, and this arises from it, that means that the universe is expanding. Okay? So the redshift tells us they're all moving away. Hubble's law tells us that the universe is expanding. Let's have a look at the data plotted on a graph. So the equation is V equals h naught d. This is V plotted in kilometres per second, and this is the distance plotted in megaparsecs. So you can see we're bringing in the megaparsec here. If you draw a line of best fit for your data, all these data points, those are the distances to galaxies and their speeds. The gradient of your line of best fit is h naught. Now, because we've used these practical units here, the units for h naught from the graph come out as kilometres per second per megaparsec, and the current value for h naught is 67 kilometres per second per megaparsec. Okay, and you'll notice that you've got units of distance, units of time, units of distance here. Units of distance will cancel out, giving you just the units of time. 1 over time, sorry. So that's the first thing to note. Second thing to note, this is not SI units. You may be required to convert that into SI units, so let's do it. To convert to SI units, the first thing I need to do is convert these kilometres into metres, so I need to multiply by 1,000. Then I need to convert the megaparsecs into metres, well that's per megaparsec into per metres. So I divide by 3.1 times 10 to the 22. When I do that, do my 67 times 10 to the 3, divide by 3.1 times 10 to the 22, I get 2.2 times 10 to the minus 18 per second. Okay? So the SI unit is per seconds there. That's the value for h naught. Now let's actually use that value. If the universe is expanding, and then you reverse time, the universe, the opposite of expanding, the universe will contract. And it's therefore reasonable to deduce that everything started at the same point in time. So that means there's a beginning to the universe, and that correlates with Olbers Paradox. The universe cannot be infinite and static. And so it makes sense if it's expanding. That means it's finite and it's not static. We can use Hubble's constant to calculate the age of the universe, and what we're going to see is that the age is 1 over Hubble's constant, and therefore because the age changes, actually Hubble's constant can't be a constant. It might be better to call it Hubble's variable or something like that. Anyway, let's get started with this. We just found that h naught is 2.2 times 10 to the minus 18 per seconds. So if we assume that the galaxies have been moving at a constant speed, which would be h naught times d, according to the equation, and if they started at the same position, i.e. when d equals 0, that's what we'll use to solve the problem. Now we have to assume that the galaxies have travelled at constant velocity, but because we've only been taking measurements for a short period of time in terms of life of the universe, that's going to be quite difficult to corroborate. And then also you have the problem with the fact that when we observe distant galaxies, it has taken a lot of time for that light to reach us. So that all of our data is well out of date by the time we actually get around to making these measurements. So I don't know exactly how the corrections for that out of date data is factored in, but there must be a way to do it. So anyway, those are some problems. Also, there is the theory of cosmic inflation, and if that's true, then the galaxies haven't been travelling at constant speed. But we're going to assume they've been travelling at a constant speed of h0d, and we'll see what age comes out from that. Okay, so we travel distance d at h0d. We use the v equals d over t equation, so the constant speed equation. The time is going to be the distance divided by v. So time is distance d over h0d, which is the speed. That gives us 1 over h0. And then we put in our value. Now bear in mind that this 2.2 times 10 to the minus 18, that's in per seconds, right? So we get a value 4.5 times 10 to the 17 seconds. That is important when you realise you've got an answer in seconds there, okay? So if you're like, you do that calculation like, what the heck, this is way too big, it's because it's in seconds. Right, then you need to convert it into years by dividing by the value that we saw earlier, which I believe is 3.5 times 10 to the 7 seconds. Anyway, then you get 1.4 times 10 to the 10 years. Okay, so that's how you do a calculation for age of the universe. Now, let's consider more about this expanding universe. The universe is expanding, so what does that mean for how it all started? The universe started off as a singularity. That means that everything began in an infinitesimally small and infinitely concentrated point. The infinite temperature and pressure caused the universe to expand, and that's why it's called, because you got this starting off with incredibly high temperatures and then expanded. That's why the model is called the hot Big Bang model. Now, because of these temperatures as well, you've got very high energy radiation, gamma radiation, at the beginning. And that radiation has subsequently expanded into the microwave region. Now, that was a prediction made by Gamal, Alpha, and Hermann. So this is Gamal, who was born in Russia, but after some time eventually moved into the United States. That's Alpha, who was born in the United States. They all working in the States when they made these predictions, and then Hermann. So they made this prediction that this initial very high energy radiation has subsequently expanded as space has expanded, and it should have expanded into the microwave region. So let's consider this microwave radiation. Now, Penzias and Wilson were doing an experiment with a new type of antenna, and they were frustrated by a source of radio waves that was interfering with their testing. And they couldn't explain where this radio signal was coming from. They tried to clear up as many sources of interference as possible, including pigeon drop-ins on the antenna. What they eventually found was that it's coming from space, and it was isotropic, so wherever they looked in space it was the same. And that source of radiation is called the cosmic microwave background radiation, CMB or CMBR for short, and it corresponded to a temperature of 2.7 plus or minus 30 microkelvins. Okay, so it is pretty much exactly 2.7, and wherever they looked, you've got these tiny differences. Okay, and what they realised is that they had actually discovered the microwave radiation that had been predicted by Gamal, Hermann, and Alpha. So this cosmic microwave background radiation is evidence that supports the Big Bang model. And here's a map of the cosmic microwave background radiation. As you look out in space and measure the microwave radiation, you can see that it's very even. So it's isotropic. The colours just indicate very tiny fluctuations, okay? That 30 microkelvin. So we've seen the predictions made about the hot Big Bang model and how it's corroborated here. There's also a further piece of evidence. There's a lot of helium in the universe, more than what can be explained by the fusion of hydrogen into helium in the core of stars. Now the universe contains about 27% of helium, and the fusion of stars can only account for about 2 to 3% of that. The remaining helium must have been formed when the universe was created during the Big Bang. So that's a further piece of evidence of the hot Big Bang model. So let's look at the chronology of the Big Bang. We've got time after the Big Bang here. This is the temperature, and this is a significant feature of the universe. Now, the first couple of rows to this table are based on theory. There's no direct experimental evidence for these because the energies involved are so high that we haven't been able to experimentally verify anything that happens at those energies. Anyway, so the temperature was infinite at the beginning. It was the universe was a singularity, and all of the fundamental forces were united. Then 10 to the minus 12 seconds, temperature of roughly 10 to the 15 Kelvin. You've got gamma radiation and fundamental particles being made there. So the fundamental particles are leptons, quarks, and their antiparticles. And then 0.01, so this is the first point where you can experimentally verify that these processes happen. 10 to the 12 kelvins, quarks form protons and neutrons. So you've got subatomic particles being formed here. 3 minutes in, 10 to the 7 Kelvin temperature, protons and neutrons form the nuclei of hydrogen and helium. 10 to the 5 years, 10 to the 4 Kelvin, nuclei and electrons form atoms, and that means now with these electrons being taken up into the atom, the universe became transparent, so the electromagnetic radiation could flow more freely. That's what we mean by that. 10 to the 6 years, that's 4,000 Kelvin, stars, galaxies and galactic clusters begin to form, and then we get to 15 times 10 to the 9 years, temperature is about 2.7 Kelvin, that's now. Okay, so that is a chronology of the Big Bang, and then what is there in the universe now? 4% is visible matter. That is stuff that we can see. Either emits light or it reflects light. So 4%, that means 96% of the universe is stuff that is not visible matter. Okay? And actually is stuff that we don't know about yet. So this type of matter, we're talking about galaxies, stars, and then gas and dust, which is spread through what is mostly empty space. So the stuff that we can see, it's only 4% of the universe. Next up, we have dark matter, 26%. Now, this is disputed by some. Some people think that the calculations match up with observations. There's no need to invoke this dark matter. It's called dark matter because it's matter, it has mass, but we can't see it, we can't detect it, we can't actually experimentally verify that it is there right now. But the reason it's invoked is because it's there to reconcile gravity calculations with actual observations. So whether it's there or not, don't know yet. And 70% is dark energy. The reason that this is invoked is there's energy that should be there because the universe appears to be accelerating. So if you've got acceleration, you require some energy. Where's that energy coming from? It's coming from dark energy. It's dark, we can't see it, we haven't detected it yet. So 70%, that makes up the 96% of the universe that we don't know about. Incidentally, I'm pretty sure this is right. I do love the name for one of the predicted dark matter particles, which is thought to be spread throughout the universe and galaxies and streaming through us. They're called WIMPs, weakly interacting massive particles. Just love that name, that's brilliant. Alright, let's look at the visible matter then. What we're going to do is look at a star's life. You need to know about the life cycle of a main sequence star. Now this slide is the one that you need to know about. The next two, where I'll show you what happens to more massive stars, you don't need to know those for exam purposes. The star starts off as gas and dust. And there are gravitational forces between those objects because they have mass. Okay? Now notice that I'm saying gravitational forces here. I'm not saying they're attracted by gravity. So it's important that you say gravitational forces that may be required in an exam. And then they're attracted by gravitational forces, so they come together to form a nebula. The nebula then collapses due to these gravitational forces, converting gravitational potential energy into kinetic energy of the gas molecules, and that raises the gas temperature. Okay, so the temperature is starting to get very, very high due to this kinetic energy that the molecules have. They form a protostar once they reach a certain temperature. The gravitational collapse continues, giving us such high temperatures that the fusion of nuclei can begin, and hydrogen nuclei are fused into helium nuclei. When you have this fusion process going on, you have a main sequence star, and that gives out a lot of energy. Now eventually, the other thing is, notice the use of hydrogen nuclei into helium nuclei. You need to use the word nuclei, it's often underlined in mark schemes, so don't say hydrogen is fused into helium, but hydrogen nuclei are fused into helium nuclei. Now there's a limited supply of energy there because there's a limited supply of reactants. So eventually the fusion is going to, because the hydrogen nuclei runs out, then the fusion will slow down, and that means because here the outward pressure from the fusion is balancing the gravitational forces. When the fusion pressure, or the pressure due to the fusion decreases, the star will contract due to those gravitational forces. That will then cause the core temperatures to increase further, and then you can have the fusion of helium nuclei into carbon nuclei. This fusion energy will overcome the gravitational forces, causing the star to expand into a red giant. As it expands, it will cool down. That's why it turns red, but it's not cold. It just cools down from what it started off at. Then the core will contract again and form a white dwarf, and it leaves behind this planetary nebula. So the outer layers of the star are left behind as the core contracts. You form a white dwarf, very, very hot, so it's very white light, and over time that will cool down into a black dwarf. Okay, so that's the main sequence star's life. Now let's look at larger stars, but I'm just stressing again, you don't need to know this for exams. If you have a star with a mass larger than 3 solar masses, MS means solar masses, then you have several red giant phases, and how many you have depends on the mass of the star that you started off with. Okay, so you have several stages more of fusion, and then eventually it will form a white dwarf and a planetary nebula. There is a limit to how big a white dwarf can be. It's the Chandrasekhar limit, which is 1.4 solar masses. So as the star does several stages, or several red giant stages, it will be shedding mass in these nebulae. So, and then eventually when the core contracts, if it forms a white dwarf, it's going to have a mass no larger than 1.4 solar masses. To form a white dwarf, the Fermi pressure is not overcome. The Fermi pressure is there because the electrons can't be any further packed together and still remain electrons. So you have this Fermi pressure. Then you can have larger stars still. Here, if you have a really, really large star, so we're talking like larger than 8 solar masses, you have several red giant stages again, or red supergiant stages. And eventually, because of these higher energy fusion processes, you get an iron core formed. And once that happens, you get no more fusion. And then the star will collapse due to gravitational forces, but the gravitational forces are so great that they overcome that Fermi pressure, forcing electrons into the nucleus. The electrons and protons combine to form neutrons, and then this intense pressure will cause the star to explode. Now, there are two possible outcomes here. If you've got 8 to 12 solar masses, then you form a neutron star. So you've got all these neutrons formed here, haven't you? So you get a star formed that has the density of nuclear matter, extremely high. And if it's even bigger than that, then you get a black hole formed, where the gravitational field around it is so great that space-time continuum is so warped that light, electromagnetic radiation, cannot escape from it if it enters. So that's meant to be like something you can't see, because black holes you can't see directly. You can detect them if they move, if a black hole moves in front of another star, but by in front I mean between us and the star, then we can actually observe gravitational lensing. Because of the huge gravitational field, the hugely powerful gravitational field around the black hole, it will warp space, which indicates the direction or controls the way light moves, so you can actually see the shift in the light as it moves between them. So the summary is that start from a nebula, you may have an average star formed, goes through a red giant, goes to the planetary nebula and white dwarf. That's what you need to know. But if you have very large mass stars, then you can have a massive star formed here. I actually got the colour right here. So average star, slightly yellowy light. Here it's more blue because it's got higher energy. Several red supergiant phases, supernova. You can have neutron star or black hole formed. Now on to consider the geometry of the universe, and we're coming to the end here. These possible outcomes for the future of the universe neglect the influence of dark energy. So I mentioned dark energy, but these outcomes don't take that into account. So we're dealing with a finite amount of energy is what I mean by that. The galaxies are moving away from each other, so they have kinetic energy. And if we say that's a fixed amount, then we can compare it with the gravitational potential energy because of the gravitational attraction between the galaxies, the gravitational forces. Now these gravitational forces are going to act to slow down the expansion. You know, when objects with mass are moving away from each other, they've got a force towards each other, so that's going to act to slow down the expansion. You have three possible outcomes. Firstly, if the gravitational potential energy is greater than the kinetic energy for these galaxies, then you have a closed universe where the expansion will not go on forever. You can have the gravitational potential energy is exactly equal to the kinetic energy, giving you a flat universe, so the universe will continue to expand forever just. And then you have a case where the gravitational potential energy is less than the kinetic energy, giving you an open universe where the expansion continues forever and doesn't approach the limit. The determining factor for deciding which type of feature there will be is the density of the universe. And the critical density is the density of the universe which will lead to a flat universe. Critical density, rho c, and this is how you determine what rho c is. It's based on Hubble constant, Hubble variable, and G, and pi, and some other constants. But that equation is in the formulae booklet. The critical density is dependent on Hubble's constant, so the extent, how accurately you know Hubble constant means, or the more accurately you know it, more precise you know it, then the better your value for the critical density. So, if the density of the universe is larger than this critical density, that will give you a closed universe. The expansion will eventually stop, and the universe will contract back to what might be called a big crunch. If the density of the universe is equal to the critical density, then that means you've got a flat universe, the expansion will continue forever, approaching a limit. And lastly, if the density is less than the critical density, then the universe is open and the expansion will continue forever. So let's look at those on a graph. This is a size of the universe versus time graph. So the geometry will affect the age. And what the thing we know now, to some extent, is the size of the universe. Obviously, I mentioned earlier the fact that we're receiving information that's travelled through space and it was emitted a long time ago. So we're observing that galaxy there, but we don't know if it's, well, it's not there now, is it? Because that information is old, it's since moved. But anyway, to some extent, we know the size of the universe now. And if anyone knows how those corrections are made, I'm very interested to know. I have asked in a few places before, but haven't got an answer yet. Some people get very offended that I ask. I genuinely just want to know. Anyway, moving on. The size of the universe on the y-axis here, and the time on the x-axis. A closed universe, remember the expansion is going to slow down and then stop. Okay, so there's our closed universe there. Flat universe keeps expanding, but it's approaching a limit. Okay, so we're getting an asymptote forming there. Then you have an open universe. This is continuing straight there. The exact shape of that may vary depending on the relationship between GPE and kinetic energy. And this one you don't need to know, but current measurements suggest that the expansion of the universe is actually accelerating. So I'm including that one in there also. Those are 4 possible outcomes for the universe, and that would be us there. Obviously, we're taking measurements. We know the size of the universe to some extent, so they all have to meet now at the same size, because that's the thing we know. And then the ages would vary according to the model, the actual geometry of the universe. And obviously the geometry of the universe actually affects the measurements you take as well. If the universe is... Anyway, I'm not going to go into that. Right, okay, so that is the future, and that brings me to the end. I hope you found this useful, and I hope you found the other lectures useful. If you've got any questions, you can ask them on Twitter or in the comment section. And all the best for your exam. Hope it goes really well on Thursday.